A robot on Mars has been driving past white rocks for 4 years, thousands of them scattered across the floor of an ancient crater, and nobody could figure out what they were until now. In December 2025, scientists finally published their analysis. Those white rocks are made of kaolinite. It's a clay mineral. You've probably never heard of it, but you've definitely touched it. It's what makes porcelain white, fine china, toilet bowls. And on Earth, kaolinite only forms one way at the surface. Millions of years of heavy rainfall in warm, tropical conditions. Not a drizzle, not occasional flooding. We're talking 1,500 millimeters of rain per year. That's Miami levels. That's Amazon rainforest territory on Mars. Let that settle for a second. Because this isn't just another Mars had water story. We've known Mars had water for a while. We've seen the dried up river channels, the lake beds, the mineral deposits. But water can come from a lot of places. Ice melting underground, brief volcanic events, a big impact temporarily heating things up. All of those could explain channels and minerals without Mars ever having a real climate. What kaolinite does is different. Kaolinite requires rain, actual rain falling from actual clouds in an actual atmosphere for millions of years. You can't cheat your way to kaolinite. It forms when water slowly, relentlessly leaches every mineral out of rock except aluminum. That process takes an enormous amount of time and an enormous amount of water cycling through the system over and over again. So what are we really saying here? We're saying Mars had a sky full of clouds. We're saying water evaporated from lakes and rivers, rose into the atmosphere, condensed, and fell back down as rain. We're saying Mars had weather, a functioning water cycle, a climate system, for millions of years, and probably not a cold one either. Kaolinite forms best in warm conditions, 10 to 25 degrees Celsius. That's 50 to 77 Fahrenheit. That's t-shirt weather. For decades, the dominant view of ancient Mars was that it was cold and icy. Sure, maybe it had some liquid water here and there, but the mainstream picture was a frozen world where water only appeared in brief episodes. Volcanic eruption melts some ice. Water flows for a few years. Everything freezes again. This kaolinite finding is a serious problem for that model. You cannot make kaolinite in brief thaws. The chemistry doesn't work. You need sustained warmth and sustained rainfall over geological timescales, millions of years minimum. The lead researcher on this paper is Adrian Braz from Purdue University. He and his team did something really clever to prove this was rain and not something else. Because there is another way to make kaolinite. Hot water from volcanic systems underground, what scientists call hydrothermal alteration. So you could argue maybe these rocks formed near a volcano, not from rain. Braz compared the Martian rocks to 3 sets of Earth rocks. Kaolinite soils from ancient tropical environments in California and South Africa, and kaolinite from hydrothermal systems. The chemical fingerprints are different. Rain-driven kaolinite has a distinct signature. Low iron, high aluminum, specific ratios of titanium and nickel, and the Mars rocks match the rain-driven samples, not the volcanic ones. Now here's a detail that adds a layer of mystery. These white rocks are what geologists call float rocks. They're just sitting there on the surface, disconnected from wherever they originally formed. Nobody knows exactly where they came from. Maybe they were washed into Jezero crater by the river that once flowed into its ancient lake. Maybe a meteorite impact blasted them there from somewhere else on Mars. There are large kaolinite outcrops visible from orbit in other parts of Mars. But Perseverance hasn't reached any of those yet. So we have these geological orphans, evidence of a world that once was, scattered like fragments of a broken story. Let's try to piece that story together. Because if you really think about what it takes to have rain on Mars, you start to realize how different this planet must have been. Today, the atmosphere on Mars is almost nothing, 6 millibars of pressure. Earth's atmosphere is over 1,000 millibars. Mars has less than 1% of what we have. At that pressure, liquid water basically can't exist on the surface. It either freezes or boils off immediately. So for rain to fall, Mars needed a much, much thicker atmosphere. Estimates range from 20 to 100 times thicker than what it has now. Probably mostly carbon dioxide, with water vapor and maybe some other greenhouse gases like sulfur dioxide or hydrogen. A thick blanket of air, trapping heat, keeping the surface warm enough for liquid water. And if you had that atmosphere, the sky would have looked different too. This is something most people don't realize. With a thick carbon dioxide atmosphere, Rayleigh scattering works the same way it does on Earth. Blue light gets scattered more than red light. Ancient Mars probably had blue skies, maybe blue-gray on overcast days, with white clouds drifting across. Not the butterscotch pink sky we see today. That color comes from fine iron dust suspended in the thin modern atmosphere. 4 billion years ago, before all that oxidation happened, before the rust formed, the sky was probably something you'd recognize, something almost familiar, and the surface. Imagine standing at the rim of Jezero Crater. Below you, a lake stretching about 50 kilometers across, twice the size of Lake Tahoe. A river flowing in from the west, building a delta where it meets the lake water. The rocks around you aren't red, that rusty color Mars is famous for. It developed over billions of years of UV radiation, breaking apart minerals and oxidizing iron. Back then, the rocks were probably dark gray basalt, volcanic rock, with patches of bright white clay where the rain had been doing its work for ages. No plants, no trees, no green anywhere. But maybe in the shallow waters near the lakeshore, thin films of something, microbial mats, brownish, maybe purplish, maybe nothing visible at all. We don't know. And in the distance, volcanoes. Mars had the biggest volcanoes in the solar system. Olympus Mons was still building during this era. 22 kilometers tall, almost 3 times the height of Everest. Plumes of gas rising into that thick atmosphere, feeding it, maintaining it. A living geological system keeping the planet warm. Both Mars and Earth, around 4 billion years ago, would have looked surprisingly similar from space. 2 rocky worlds with thick atmospheres, liquid water on their surfaces, active volcanoes, no free oxygen, both getting pelted by meteorites during what we call the late heavy bombardment. If an alien spacecraft had flown through our solar system at that time and looked at both planets, they might have bet on Mars. It was doing everything right. And this is where the story gets genuinely unsettling. Because here's the timeline. Mars had its warm, wet period during what planetary scientists call the Noachian, roughly 4.1 to 3.7 billion years ago. That's when the kaolinite was forming. That's when the rain was falling. That's when Jezero's lake was full and rivers were carving valleys across the surface. On Earth, during that exact same window, life was emerging. The earliest widely accepted evidence of life on Earth, stromatolite fossils in Greenland, dates to about 3.7 billion years ago. Some researchers push it earlier. There are controversial structures in rocks from northern Canada that might be biological, dating to 4.28 billion years ago. If that's real, life on Earth appeared within maybe 200 million years of stable liquid water. Maybe less. 200 million years sounds like a long time, but in geological terms, that's fast. That's suspiciously fast. It suggests that once conditions were right, once you had liquid water and the right chemistry and enough time, life didn't take long to show up. Almost like it was inevitable. Almost like it was easy. And Mars had those same conditions. For millions of years, during the same era, with the same basic chemistry, the same building blocks, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, all present on Mars, all available in an environment with warm liquid water cycling through rock, exactly the kind of place where the chemistry of life thrives. So the uncomfortable question is this: if life appeared on Earth almost as soon as it possibly could, and Mars had essentially the same setup running at the same time, what are the odds that absolutely nothing happened on Mars? We have exactly one example of life starting from scratch, Earth. And in that one example, it happened fast. Now you can interpret that 2 ways. Maybe life is easy. Given the right conditions, it just happens. Chemistry does its thing, complexity builds, and eventually something starts reproducing itself. If that's the case, Mars almost certainly had life. Or maybe Earth got extraordinarily lucky. A 1 in a billion chemical accident that just happened to work out. And Mars rolled the dice and lost. We genuinely don't know which interpretation is correct. We have a sample size of one, but that one sample is suggestive, very suggestive. And there's another wrinkle that makes this even more interesting. During that late heavy bombardment, when asteroids and comets were slamming into both planets, the impacts were powerful enough to blast rocks off the surface and send them flying through space. We know this actually happens because we have Martian meteorites on Earth right now, over 300 of them. Rocks that were knocked off Mars by impacts, drifted through space, and eventually fell to Earth. If life existed on early Mars, those rocks could have carried it here. Bacterial spores can survive in space. They can survive the heat of atmospheric entry. They've survived on the outside of the International Space Station for years. The transfer between planets isn't the crazy part. The question is whether anything was alive to make the trip. If it was, there's a real possibility that life on Earth didn't start on Earth, that the first living things on this planet were immigrants from Mars, that you, me, every living thing on Earth descends from Martian microbes that hitched a ride on a rock 4 billion years ago. We might all be Martians, and we might never have known if a rover hadn't rolled past some white rocks in a crater on a dead world. Or maybe it went the other direction. Maybe life started on Earth first and seeded Mars. Or maybe life started independently on both planets. Or maybe life never appeared on Mars at all, despite having every opportunity. Every one of those scenarios is consistent with what we currently know, and every one of them is profound. But here's what makes the kaolinite discovery specifically important for this question. Previous evidence for water on Mars could always be explained away as brief, cold, hostile, underground aquifers, flash floods from ice melting. Not the kind of environment where you'd expect life to get a real foothold. Kaolinite tells a different story. Kaolinite says this was a warm place, a sustained place, a place where water cycled through the environment continuously for millions of years. That's not a puddle in a desert. That's a habitat. That's the kind of environment where life on Earth was doing just fine. So what happened? What killed Mars? Mars is small, about half the diameter of Earth, a tenth of the mass, and that matters more than almost anything else about a planet's long-term fate. Smaller planets lose their internal heat faster. They cool down. And when the interior cools enough, something critical stops. The dynamo. Deep inside Mars, there was once a liquid iron core churning with convection currents. That churning generated a global magnetic field, just like Earth has now. That magnetic field was a shield. It deflected the solar wind, a constant stream of charged particles blasting out from the sun at hundreds of kilometers per second. Without a magnetic field, the solar wind hits the atmosphere directly, and it strips it away, molecule by molecule, year by year, over hundreds of millions of years. Around 3.9 billion years ago, give or take, Mars' core cooled enough that the dynamo stopped. The magnetic field collapsed, and the slow death began. The solar wind started peeling away the atmosphere. As the atmosphere thinned, the pressure dropped. Water couldn't stay liquid anymore. Temperatures fell. The rain slowed, then stopped. Rivers dried up. Lakes froze. Then the ice sublimated, turned directly from solid to gas, and that gas was stripped away too. NASA's MAVEN spacecraft has been orbiting Mars since 2014, and it's directly measuring this process happening right now. Even today, the sun is still stealing what's left of Mars' atmosphere, about 100 grams per second. It doesn't sound like much, but over 4 billion years, it adds up to oceans. Mars didn't die from a catastrophe. No asteroid wiped it out. No supervolcano poisoned it. Mars died from the inside out. Its heart went cold. And without that internal heat driving a magnetic shield, the sun slowly, patiently, over hundreds of millions of years, stripped away everything that made Mars alive. The atmosphere, the warmth, the rain, the water. All of it stolen by the same star that once made it all possible. And if anything was living on Mars when this happened, it would have been a slow apocalypse. Not sudden, not dramatic. Just things getting a little worse, generation after generation. A little less rain, a little colder, the lakes shrinking, the rivers thinning, the habitable zones contracting toward the equator. then toward the deepest valleys where atmospheric pressure held out longest, then underground, into aquifers, into pockets of liquid water beneath the frozen surface. Maybe life held on down there for millions of years after the surface became uninhabitable. Maybe it's still down there. We genuinely don't know. The samples Perseverance is collecting right now, sealed in titanium tubes and cached on the Martian surface, are specifically chosen from locations where ancient life might have left traces. Those tubes are waiting to be picked up by a future mission and brought back to Earth. When that happens, we'll be able to analyze them with instruments far more sensitive than anything a rover can carry. We might find fossilized microbes, chemical signatures of metabolism, evidence that Mars was once alive, or we might find nothing. And honestly, that would be almost as interesting. Because if Mars had warm water for millions of years during the exact window when life emerged on Earth and nothing happened, that tells us something important too. It would mean life is harder to start than we think. It would mean Earth really did get lucky. It would mean we might be far more alone in the universe than the optimists hope. Either way, those white rocks in Jezero crater have changed the question. It's no longer, did Mars have water? It's no longer even, was Mars habitable? The question now is, was Mars inhabited? And for the first time, that question doesn't sound crazy. 4 billion years ago, rain fell on Mars. Warm rain. From clouds and a blue sky. It fell on dark volcanic rock and slowly, over millions of years, washed away everything except white clay. Then Mars died. The rain stopped. The sky turned pink. The rivers vanished. And for 4 billion years, those white rocks just sat there, waiting, until a little robot from Earth rolled up and figured out what they meant. The next sample return mission could answer the biggest question humanity has ever asked. Did life start more than once? And if it did, everything changes. If you want to keep up with the latest discoveries that are rewriting what we know about our place in the universe, there's always something new. And lately, the new stuff has been wild.